This video is going to be covering multiplying and dividing common-based exponents. I've got common-based capitalized because this only works when you have common-based exponents. Before we get into it, I want to talk about some review. If you've watched the Powers of 10 video, you should remember that any number to a negative exponent is the same thing as 1 over that same base, but to a positive exponent. We talked about it with powers of 10, but it also works for any base. Any 2 to the negative 7 is the same thing as 1 over 2 to the 7th. 8 to the negative 4 is the same thing as 1 over 8 to the 4. That's going to come in handy as we go through these. First, we're going to talk about multiplying exponents. When multiplying exponents with the same base, you just add the exponents. So we have 3 to the power of 4 times 3 to the power of 5. That's the same thing as 3 to the 4 plus 5, which works out to 3 to the 9th. So we just add the exponents and we get 3 to the 9th. Now once again, I want to point out this only works for exponents with the same base, and you're multiplying. If you have something like this, it's not going to work because those are not common bases. They're not the same base. Bases are not the same. You have to work that one out the long way. So here's proof of why this works. So we have 3 to the power of 4 times 3 to the power of 5. When writing this out as a product of factors, 3 to the power of 4 would be, you'd write down 4 of the number 3 multiplying by itself. And then you'd write out 5 of the 3's on the other side. So we're multiplying a whole bunch of 3's. How many are we multiplying? We're multiplying 9 of them. So that's the proof of why this works. So we're going to do some practice. This would be a good time to do like a pause or a screenshot if you wanted to work these out on paper. Pause it, try to figure these out, then we'll talk. I want to point out that this says simplify each expression, leave an exponential form. So that means you don't have to work it out all the way. You can leave it in exponential form. That's real nice because you don't have to do 8 times 8 times 8 times 8 times 8 and then figure it all out. You just leave it in exponential form. So we have 8 to the 3rd times 8 to the 7. You're going to just add the exponents, 8 to the 10. You're done. Let's look at this next one. 2 to the 19 times 2 to the negative 7. Well, it's kind of weird because we have a negative exponent. We're not going to worry about making it into 1 over 2 to the 7th. What we are going to do, though, is just rewrite it. We're going to think of it as 2 to the 19 plus negative 7. Well, when you're adding a negative, that's the same thing as just subtracting that number. So 2 to the 19 minus 7 works out to 2 to the 12th. You're done. 7 to the 9 times 3 to the 2nd. We can't do anything with them. They don't have common bases. So for this last one, we have 3 to the 12th times 3 to the 8. They do have the common base. We can do 3 to the 12 plus 8. And there you go, 3 to the 20. So that's multiplying. You leave them in exponential form. If they said work it out to a standard form number, then you'd have to work them out all the way. You'd have to do, 8 times 8 times 8, a bunch of 8's. Down here you'd have to do a bunch of 2's and multiply them. Luckily, you get to leave them in exponential form. Dividing exponents. Well, when we were multiplying exponents with common bases, you had to add their exponents. With division, when dividing exponents with the same base, you subtract the exponents. So 3 to the 8th divided by 3 to the 2nd is going to work out to 3 to the 8 minus 2, which is 3 to the power of 6. 5 to the 4th divided by 5 to the 10th. This is where things can get a little bit weird. You still think of it as 5 to the 4 minus 10. If you remember your integer rules, that's going to be 5 to the negative 6. Sometimes they'll say you can just leave it with negative exponents, but if they say they only want positive exponents, you'd have to rewrite this, and this is where you want to remember that whole negative exponent rule, where any negative exponent is the same thing as 1 over 5 to the 6th. If they say positive exponents only, you'd want it in that final form as a fraction. So we're going to do a few more. This is a division problem still. It's written in different form, but this is still division. So 2 to the 5 over 2 to the 2nd. You can rewrite that as 2 to the 5 minus 2. It's always going to be the top exponent minus the bottom exponent. Works out to 2 to the 3rd. Let's do another one. 7 to the 3rd over 7 to the 9. You're going to think of it as 7 to the 3 minus 9. You get 7 to the negative 6. Or you could rewrite it as 1 over 7 to the 6. Either of those bottom two would work. This one or this one. Here's the proof of why it works. If you have 5 to the 5th divided by 5 to the 3rd, you could also think of it as 5 to the 5th over 5 to the 3rd. And if we think about multiplying of common bases, we could think of this as the top portion, 5 to the 3rd times 5 to the 2nd, is the same thing as 5 to the 5th. And I'm going to go ahead and apply my identity property down here. And I'm going to think of this as 5 to the 3rd times 1. Now the reason why I'm doing this is because we're going to go look at this 5 to the 3rd over 5 to the 3rd. And what happens is anything divided by itself basically is 1. So they're pretty much eliminated from this problem. You don't have to consider them anymore. They divide out by 1, and so we're just left with this 5 to the 2 over 1, which is just 5 to the 2 over 1, which simply is 5 to the power of 2. A little bit of a weird concept. The big thing you need to remember, if the proof is hard to understand, subtract the exponents. That's the gist of it. So here's another proof. If you have 6 to the 3rd divided by 6 to the 10, you can think of it as 6 to the 3 over 6 to the 10. So I'm going to go ahead and keep the 6 to the 3rd up there because that was the smaller exponent. I'm going to break down the lower exponent, the denominator, into something with 6 to the 3rd because we're going to look to cancel these out. 6 to the 3rd times 6 to the 7 is 6 to the 10. That's why I'm breaking it apart there so I can divide out those two. So we're left with 1 over 6 to the 7. And if they wanted it written without fraction form, you could rewrite it as 6 to the negative 7. We're going to go ahead and practice some now. We're going to go ahead and do, if you want, pause it, try to work them out on your own. And here we go. We have this first one. Common bases are good, and you basically think of it as 8 to the 3 minus 7, which works out to 8 to the negative 4, but if they are asking for positive exponents only, you can think of it as 1 over 8 to the 4th. Let's look at this bottom one. Now, a lot of kids are going to want to immediately go 19 minus 7, or minus negative 7, but you can't do it because they do not have the common bases, so you leave that one as it is. You could think of this as 2 to the 19 times 1 over 7 to the 7, but basically you can't do much else with it. So let's look at this one. 3 to the 9 divided by 3 to the 2nd. Everything checks out, common bases. Should be pretty easy at this point. 3 to the 7. Then you have, finally, another division problem, except you just have it in fraction form. 5 to the 7 over 5 to the 4th is going to be 5 to the 7 minus 4, which is 5 to the 3rd. Now, once again, you get to leave this in exponential form, so they all stay as they are. You don't have to work them out to make them into giant numbers with a lot of digits. Hope this helps. Best of luck to you.